we will continue with the calculations of multi-level systems having a fixed energy. So, we still remember that we are still talking about distinguishable particles. By that what we mean is that they are classical particles which can be distinguished. I would like to emphasize one particular point here is that it is not our ability or inability to distinguish a particle as distinguishable or indistinguishable categorization. It is the statistics that comes out of the particular experiment that will eventually tell us whether particles are distinguishable or indistinguishable. So, what I mean by that is that one can do some mathematical calculations with distinguishable particles in distinguishable cells or in this indistinguishable particles in distinguishable cells, and they will eventually give rise to different statistics. Now, when you do an experiment and see that it is following a particular type of statistics, then we know for sure that it is the which category of particle we are talking about, and you will see that today following a few slides will bring up that particular issue, that the experiment itself dictated that what kind of particle we are talking about with the background mathematical foundations for understanding them. So, briefly just summarizing what we talked about with 3 particle and 3 levels, 3 units of energy, not 3 levels, 3 units of energy. Here their levels are 4, 0, 1, 2, 3, and there are 3 possible distributions, and the total number of microstates that came out of that is 10, and we know that it is a star bar kind of problem where indistinguishable particles go into distinguishable cells. Here indistinguishable particles means energy. So, we are distributing energy which are indistinguishable. We do not know whether blue energy or green energy or anything, they are all indistinguishable energy units which is going into distinguishable particles meaning cells. So, again we can map it whichever way we want to. So, and that star bar problem with 3 particle and 3 units of energy will give rise to the value of 10, and you can do that calculations simply by. So, you know the formula for a star bar problem, that is number of energy unit is R, particle is n minus 1, C n minus 1. So, R is 3 here. So, 3 plus 3 minus 1, C 3 minus 1, which is 5 C 2, and that is nothing but 10. So, those are the 10 the total distributions that are here, and individually. So, the 3 plus 6 plus 1 is 10, and individually one can get the 3, 6 or 1 by using the multinomial distributions, where you use n factorial the total number of particle by n 1 factorial, n 2 factorial, n 3 factorial and things like that. So, you can see that this 3 is coming from capital N is 3 here, where n 1 is 1 and n 2 is 2. So, you can get 3 factorial by 1 factorial and 2 factorial, and you will get the number 3. In this case, you will get 3 factorial by 1 factorial, 1 factorial, 1 factorial, which will give you 6. Here you will get 3 factorial by 3 factorial, 0 factorial, 0 factorial, and you will get 1. So, that is how we are getting A, B, C, and that is we are getting because they are all distinguishable particles, as you can see from the color itself. And we also talked about that the B is the most probable distribution, because probability of this particular distribution, which is obtained from the number of microstates of B, which is 6, divided by total number of microstates, which is 10, and that gives us 6 by 10, which is the most probable distribution, or MPD in short form. Now, this is just 3 particles and 3 units energy levels, 3 units of energy, not 3 energy levels again, this 3 units of energy that we are talking about. And we are going to go little bit more complicated system of having 5 units of energy and 4 particles, and this also we talked about that you can get these 5 possible distributions, 6 possible distributions, and each of them is having different number of microstates. Now, I already mentioned that the number of distributions you can get by partitioning an integer into that many number. For example, here the number of units of energy is 5. So, you partition the number 5 into 4 parts. So, you are partitioning 5 into 4 parts in order to get the number of distributions of having 5 units of energy into 4 particles. So, basically you are partitioning the 5 into 4 parts such that your each part is some energy unit for a particle. So, let us say if you break 5 into 1, 1, 1 and 2, that means you are giving 1 unit of energy to one particle, another 1 unit of energy to another particle, another 1 unit of energy to another particle and 2 units of energy to the last particle. If you break it into 3, 2 and 0, 0, then you are giving 3 units of energy, will give you 6 partitions. So, 6 partitions essentially is 6 distributions. Now, 6 partitions can be of different kind. For example, as I said that when I am partitioning 5 units of energy into 6 partition, one of the partition can be 3, 2, which means that one particle is getting 2 units of energy, another particle is getting 3 units of energy, another particle is getting 2 units of energy and rest of the particle are getting 0 units of energy. So, that is one type of distribution. One can break the 5 into 1, 1, 2 and 1, let us say. So, 3 particles are getting 1 units of energy, one particle is getting 2 units of energy and that is what it is, one distribution. We can break 5 into let us say 3, 2, 2, 1 and 0. So, in partition you will not get the 0. However, you have to see that whether it is less than the number of particles or not. If it is, then that last one is getting obviously the 0 units of energy. So, this is another type of distribution. So, in order to get the number of distributions, we need partitioning of the that integer, which is equivalent to the amount of energy. For example, partitioning 5 into 4, P 5 4 is number of partitions of 5 up to 4 parts, up to. So, there can be a partition of like only 5. So, that 5 will go to only one particle and the rest of them will get 0. So, up to 4 parts, that is the more important thing 5 4 means. So, and now for each of the distributions, for example, distribution A, we know how to calculate the number of microstates, that is factorial n by n 1 factorial, n 2 factorial and things like that. And if you do that, then you will get here 5 factorial by 3 factorial and 1 factorial give you number 4. So, no sorry, it is 4 factorial. So, number of particles, total number of particles is 4. So, 4 factorial by 3 factorial and 1 factorial will give you 4. Here 4 factorial by 2 factorial, 1 factorial, 1 factorial will give you 12 and things like that. Thus, we will get the individual number of microstates for individual distribution, and of course, the total number of microstates you can get by the formula that is given for star bar system, which indicates that indistinguishable particles putting into distinguishable cells. So, now that is exactly given here. For example, this is the formula for getting total number of distributions, and it is mentioned here that if r equal to 5 and n equal to 4, we get 56 possibilities, total 56 possibilities. So, all microstates combined, all microstates of all distributions together will give you 56. So, we can call that as W tot, total number of microstates. Now, if our units of energy is 3, number of particle is 3, then total W tot we are going to get as 10, as we have shown before, and that is again shown in this particular diagram, where 3 indistinguishable particles, i.e. energy, is distributed among 3 distinguishable cells, i.e. particles, and we can see all the 10 for 3 particle and 3 boxes. Now, let us go to a little bit more complicated system, and let us now distribute 7 units of energy into 9 particles. Again, if I have to tell you that how many number of distributions are there, I would partition 7 into 9 parts. Now, 7 cannot be broken into 9 parts. So, effectively P 7 9 is basically nothing but P 7. That means, partition the number 7 to all possibilities, and that number is going to give you 15, as you can see from Mathematica, or you can do it yourself and you can see that. I will give you some example for, let us say, if you have 7, then how many partitions are possible? You can get 7, only 7, which means all one particle is having 7 units of energy and all particles are having 0 units of energy. You can also have 6 1, which means one particle is having 6 units of energy, another particle is having 1 units of energy and everything else 0. You can get 5 1 1, you can get 4 1 1 1, you can get 3 1 1 1 1, you can get 2 1 1 1 1 1, 5 ones basically, and you can get all 7 ones, 1 1 1 1 1 1 1 1 2 3 4 5 6 7. Okay. So, there are more possibilities. One possibility will be that you can do 5 2, that means one particle is having 5 units of energy, another particle 2. You can do 4 3, you can do 4 2 1, you can do 4 1 1 1 is already done. So, that you cannot do. Then you can do 3 1 1 1 is already done. So, but 3 2 5 2 you can do 3 2 1 1, and you can do 2 2 4 5 6 7, you can do, and 2 all ones are already done. So, let me see how many are there. So, 1 2 3 4 5 6 7 8 9 10 11 12 13. So, 2 more are remaining. Let me find out. So, 4 triple 1 is already done, 3 2 2 are done, 3 2 1 1 is done, 2 2 1 1 1 is done, 3 3 1 is remaining. Anything else? 2 2 2 1 is not done. Okay. Now, let us count how many. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. So, thus we got all 15 possible distributions. So, each one is a distribution that you have to understand. Let us say I can call it A, I can call it B, I can call it C. So, each one is a distribution, each one has a number of microstates associated with that for distinguishable particles. Now, let us go back and see how we can do that. So, this is our energy distributions from 0 to 7, because there are 7 units of energy, not more than that, and there are 9 particles. So, now this is one particular distribution in which I have to put the particles. So, let us start with giving one particle all amounts of all the energy, and then we can build up the other things. So, I give 1 units of energy, 7 units of energy to one particle, and 0 will automatically go to the rest of the particle. So, the distribution will be 1 and 8. Now, how many possible microstates can be there? It will be simply factorial 9 by factorial 8 and factorial 1, which will give us 9. Now, let us go to the second one, in which I have brought down the energy of one particle by one level here. I have brought down energy of level by level 1. Similarly, I have to pull up one particle to the next level. You see, so now it has become 7. It is 1 1. Now, how many number of possibilities will be in this case? 9 factorial by 7 factorial and 1 factorial. Now, go to the third distribution. I bring down this particular one by one more step, and automatically I have to pull this one up by one more level. So, again that is 7 1 1, and it will have the same number of microstates. Now, let us go to the fourth one, distribution. This one let us keep in the same level, but I bring this one down by one level. So, I have to pull up one particle to the higher level. So, it becomes 1 to 6. This will have factorial 9 by 6 factorial, 2 factorial and 1 factorial number of microstates. So, similarly, I have 711, I have 1116. So, this is where you can actually get the number of possible distributions. So, you bring down this particle by one level and put one particle up. For example, here we brought down one and I pulled up to 1. So, now even if you miss it, that is why I already discussed that if you miss it by this way, you can always get by the partitions way and confirm whether your number of distributions are matching with this particular way or not. So, now I get G, H and all the other distributions as it is mentioned here. And this is a all 15 possible distributions that are possible and that is mentioned here. I will just remove this because I will show you the number of possibilities for each one below. So, we have shown that how the 9 comes. Similarly, 9 factorial by 7 factorial and 1 factorial will give you 72. The C is also 72, D is 252 and things like that. And if you see here, this is the largest number 1512 and that comes from 9 factorial by so this is jth one is this one. So, 9 factorial by 5 factorial, 2 factorial, 1 factorial and 1 factorial will give you 1512 because you can show I can show it here 9 into 8 into 7 into 6 divided by 2 factorial, because we can take care of the 5 factorial already we took care of. So, now 2 cancels and give us 3. So, it is 9 into 8 72 into 7 into 3. So, 72 into 21 1512, that is what we get as the number of possible distributions for the jth one. It is just shifted a little bit. So, please look at this way, the O1 is 36. So, you see now that if I add up all the number of distributions, then that is the number that I am going to get by summing up these individual distributions. By summing up these individual distributions, the microstates of individual distributions, and I can get the W tot, which also I can get from the star bar formula, that I have 9 units of energy, 7 units of energy in 9 particles, which means 7 plus 9 minus 1, it is r plus n minus 1, C 9 minus 1, which is 15 C 8, and that will give me 6 4 3 5. I will just do the calculation, 15 C 8 6 4 3 5, that is what we are going to get from this thing. So, we can get all possible distributions just in using one formula itself. However, for individual distributions we have to distribute the particles in different level and then calculate it. It is also mentioned here. Now, can we continue for larger and larger systems like this? How do we know the energy levels and how do we know whether energy is equally spaced or not, and that is the thing that you have to consider, and can you estimate all possible microstates. So, we will come back to these questions, but with some more examples. Now, here is a summary. So, number of partitions is number of distribution, number of distributions is can be partition 7 9, 7 into 9 partitions maximum, and then total number of microstates can be given from this particular formula, and for actual for an individual distribution, for I would say individual distribution, or for a particular distribution, we can calculate the W from this particular formula. So, for the distribution A, we can get by using this particular formula. And now, we have to estimate one more thing. We have to estimate that what is the number of microstates possible when a particular particle has having ith energy, because we want to know that how many particles are having ith energy, energy I. So, we can show that, but I can explain to you briefly that in all possible microstates if I want to calculate that how many particles will have energy I. So, in order to calculate that, what you can do is that let us say the total number of energy, total units of energy is N0, and I can take out I units of energy and give it to one particle. So, I am left with N0 minus I amount of energy, and I am left with N minus 1 particle. You see, earlier I had N0 amount of energy and I had N particle. I have given I amount of energy to one particle. So, my energy units reduces by I and my number of particle reduces by 1. So, that means now I have a different problem to solve. I want to solve that for N0 minus I units of energy and N minus 1 particle, how many possibilities are there, and that is nothing but this particular formula N0 minus I plus N minus 1 C N minus 1, which is giving me precisely this particular formula, that N0 plus minus I plus N minus 2 C N minus 2. So, I will just write it once more here. It will be N0 plus N minus, sorry, this is I, N0 plus N minus 2 minus I C N minus 2. So, by using this particular formula, we are going to get the number of particles that are there in the ith energy level. Now, once we use this particular formula, we can calculate that Ni is the number of particles in the ith level, which you can get from the number of microstates corresponding to that particular state where the particle is in the ith level, divided by the total number of W and multiply by the total number of particles. Now, Wi by W, we can say that it is the probability of that particular state. So, that is nothing but Pi. So, Pi into N is Ni, which means Ni by N is nothing but Pi, right. Is it part clear? So, what I will write it again here, Ni equal to N into Pi. So, which means Ni by N is Pi. So, probability of a particular state I to be occupied, ith energy state to be occupied is Ni by N. It is given by the number of particles that is there in the ith energy level divided by the total number of particles. So, N is the total number of particles. How did I get that? We got that by also calculating the number of microstates corresponding to the particle having ith energy divided by total number of microstate. So, that is so basically we can say that this is nothing but W I by W. So, Ni by N is nothing but W I by W. So, and we have given the formula of W, we have given the formula of Wi, and that when you use for 5 units of energy and 4 particles, you see it is following some kind of decaying distribution. What it means is that when my energy is smaller, when the energy is smaller, Ni is bigger, larger. So, Ni is larger means probability is larger. So, for particles to fill up the lower energy level is more probable than higher energy level. You see the number of the probability. So, this is Ni, or I have written here Nj by N, it is same as Ni by N. So, you see the number of particles or probability of particles filling up higher energy level is less. So, this is nothing but probability, it is nothing but P j, we are denoting it by j. So, I and j are dummy symbols. So, we are denoting by j. So, the probability of particle occupying jth level, and here it is energy E j. So, as the energy increases, for example, here the 5 units of energy and 4 particle, as the energy increases to from 0 to 5, the probability decreases. So, which means that it is less and less probable for the particle to occupy higher levels. So, there will be more particle in the lower level, then less particle, then less, then less, then less. So, it will continuously decrease as the energy goes higher and higher. Remember, initially when we talked about distribution of particles, there was no energy constraints involved. If there is no energy, then particles are equally occupied. We have shown you that for two level systems, when there is no energy, we showed you that the most probable distribution is when the n by 2 particle is there in one state and n by 2 particle in another state. The reason is that time there was no energy constraints involved. The energies of both the systems were same. So, that they are called degenerate state basically if the energies are same. Now, even if if energies are same, then particle will like to occupy equally. However, we have shown that when the energies are not same for different levels, then this probability calculation, just by the calculating the number of microstates itself, just by how we can distribute this total amount of energy into particles, just the number of possibilities. So, what we did when we calculated the 15 possible distributions and 6435 number of possible microstates. So, we have all 6435 possibilities are there, and what we have done till now is that we have just distributed the particles and to satisfy the total energy. So, we have satisfied the constraints of two things. One, we have satisfied the total number of particles remain same and the total energy should be also same. With that constraints, when you distributed the particles, what we finally landed up is that the higher level energy level will occupy with lesser probability, and that is what is shown in this particular graph using 5 units of energy and 4 particles, and the formula for getting that is given here. So, this W will give you all possible microstates combining all distributions, and this Wi will give you the probabilities of a particle occupying ith or number of microstates in which a particle will occupy ith energy level. When you do that, you get this particular one. Similar calculation have been done for other systems as well. 7 units of energy and 9 particle, we have discussed you and we have seen that in this particular case there were. So, in this particular case our W tot was 56, and in this particular case our W tot was 6435. We did not calculate individual Wi's though. If you want, you can calculate that using this particular formula, which we have done it, and that is how we plotted this graph. Again here you can see we are plotting Pj against Ej, energy of the jth level, and you see it is decreasing as the energy increases. You see it just keeps on decreasing. When the energy is 7 units, it is very less probable. So, automatically it is distributed in such a way that lower level will have higher number of particles and higher level is this. Now, here we have just switched the number of units of energy and particle. Here 9 units of energy is given to 7 particles. So, more energy, less number of particles. Here there was less energy, more particle. Yeah. So, you see here also is the same case where this is decreasing as the energy increases. So, all 3 graphs show the same pattern. Now, remember we are dealing with very few number of particles and few energy states. In actual situation there will be again 10 to the power 23 number of particles and maybe even larger number of energy states. So, there of course, the statistics will be much better. Here even with such a simple such a small number of particles and such small units of energy, we can still see a pattern. What kind of pattern it is? In order to know that, we have fitted this to some numerical equations, and that equation is typically an exponential equation, because that is an exponentially decaying graph, we can visually see that. So, we try to fit that to this particular exponential equations a e to the power minus b E j. So, this E is energy E, this E j. So, it shows that if E j is higher, if this is larger, then this term will be smaller, and therefore, this term also will be smaller. This is called an exponential decaying graph. A is something like a normalization constant, which means when E j equal to 0, then this quantity will become 1 and it will give you A, that is called normalization constant for the 0 energy value. Now, we fitted this graph to this blue line shows the fitting. You see that it fits beautifully and it gives 0.387 and 0.434. What is the significance of that? That means when the energy is 0, then the Ni by Nj probability will be 0.387, and you see here it is very close to 0.35, A is 0.35, and this B 0.434 indicates that how fast the decay will happen. If B is larger, then it will decay much faster. If B is smaller, then it will decay slowly. So, look at this 7 units of energy and 9 particle. Here at 0 energy the probability is 0.537, you see it is very close to that value, and the fit is also looks much better, and B is larger. So, it falls faster. So, it decays much faster and it decays to 0. So, with more units of energy and more number of particles, it is decaying faster, and but again here you can see that the decay rate is almost similar, and A and B are given here, and this also fits very well for 9 units of energy and 7 particle. So, all of them follow an exponential distribution. So, what did we learn? That we learned that when there is no energy bias, that means the energy is not constraint is not there, then the distributions will be equal or flatter. When there is an energy constraints involved, for this kind of particles which are distinguishable particles, we see an exponential decaying distributions. These are examples coming from the one that we have tried: 7 units of energy, 9 particle, 9 units of energy, 7 particle, 5 units of energy, 4 particle. This is how we constructed it, we calculated it, and then we plotted it. However, we need to find much more general formula for that, and we will come back to that. And also one more thing you have to note down is that this we are talking about for this statistics we are talking about for distinguishable particles, where the particles can be distinguishable and they are typically called classical particles, and this distribution is known as Maxwell-Boltzmann distribution. We will talk about that little bit more, and we will show you how to find a more general formula about it. But remarkably, this by using this small number of particles and small number of energy level itself, we can see that there is a bias towards lower energy level already for the particle to be there, and it is not unequal distributions, and that has great implications in all the thermodynamic observations that we see. This probability will dictate all properties that you observe, because those properties will be averaged over by this probability itself. That means, the lower one, the properties given by particles in the lower energy level will be more weighted, more important than the properties that we get from the particles which are in the higher energy level. So, and so you will come to know later on that this B is not just simply a constant. The B is associated with the temperature, and B is in fact 1 by kBT, 1 by temperature. So, Kb is some Boltzmann constant, which will come to know that, and then essentially what you are going to get is that Nj by N will be nothing but A e to the power minus Ej by kBT. We will come back to that later on, but so B is 1 by kBT, that is taken in order for the other thermodynamic constraints to satisfy, but right now we have used B just as a fitting parameter, both A and B. So, we see this that from distinguishable particle the statistics turn out to be Maxwell-Boltzmann like, which means that there is an exponential distribution.